liars who've been trying to silence them shrink and they become weaker. That's the iron law of the universe. True things prevail.
Tucker Carlson, CERN just shut down and something terrifying has happened. A few years ago, no one knew what science could do to the world. And look, today we're growing at the speed of light in terms of scientific discovery. Though science is serving highly to the human race, it comes with a dark side as well, and all of us are aware of it. Tucker Carlson, an American television personality and political commentator, hosts the nightly political talk show Tucker Carlson Tonight on the Fox News channel. Tucker Carlson's a strong voice of the nation. He has strong views regarding everything happening around the world, whether it's climate change or terrorism. Since science is becoming the central element of the universe, now Tucker shifted his gaze towards CERN. He recently shared his opinions regarding CERN and clearly said that they are opening a portal to hell. The world has great faith in CERN when it comes to scientific discoveries, but let's find out what else CERN's up to and why Tucker Carlson thinks so evil of it. In order to bring together scientists and resources to investigate particle physics, European nations came together to form CERN in 1954. CERN aspired to unite scientists in the peaceful pursuit of knowledge at a time when Europe was still recuperating from the destruction of World War II. Geneva, Switzerland has served as the organization's headquarters ever since it was founded. The proton synchrotron, or PS, CERN's first significant accomplishment, was built in the late 1950s. The PS, which was finished in 1959, was the most potent particle accelerator on the planet at the time. It enabled researchers to analyze protons' collisions by accelerating them to very high energies. As a result, important discoveries were made, including the detection of novel particles like the pion and kaon. The Superproton Synchrotron, or SPS, a large-scale project launched by CERN in the 1970s, was based on the PC's success. When the SPS was finished in '76, it was even more potent than its forerunner, enabling researchers to investigate particles with higher energy and dive further into the mysteries of the cosmos. The W and Z bosons, which are the weak nuclear forces carriers, were found in 1983 at the SPS, and Carlo Rubbia and Simon van der Meer were given the Physics Nobel Prize as a result. Additionally, CERN focused on the Large Electron Positron Collider, or LEP, an even more ambitious project in the late 1980s and early 90s. The LEP was the most potent electron-positron collider ever constructed when it was finished in 1989. It ran until 2000, providing groundbreaking findings and placing restrictions on the mass of the Higgs boson, a particle thought to give other particles mass. Isn't it interesting? After the LEP was operationally successful, CERN started to work on the Large Hadron Collider, or LHC, which is its most well-known and ambitious project to date. The LHC, a 27-kilometer subterranean ring that was finished in 2008, accelerates protons or heavy ions to speeds that are very close to the speed of light. Scientists have been able to explore the fundamental properties of matter and the universe's beginnings thanks to this particle accelerator, which is the most potent ever constructed. The long-sought Higgs boson was finally discovered at the LHC in 2012 thanks to the ATLAS and CMS experiments. The Higgs field, which gives other particles mass, was proven to exist by this discovery, which also brought François Englert and Peter Higgs the Physics Nobel Prize. Since then, the LHC has carried on expanding our knowledge of the cosmos. At CERN, researchers have investigated the mysteries of dark matter and dark energy, in addition to studying the Higgs boson's characteristics in greater depth and looking for new particles outside the standard model. Not only is CERN renowned for its particle accelerators, but also for its sense of community and global cooperation. It's created an atmosphere where researchers from different countries can collaborate on cutting-edge experiments and exchange expertise. The CERN facility continues to draw top talent from all over the world and has been instrumental in educating the next generation of physicists and engineers. CERN has made contributions to technology breakthroughs in addition to its scientific research. Tim Berners-Lee developed the World Wide Web. In 1989, Lee at CERN transformed how data is shared and accessed around the world. The first website was developed and standards for web technologies were established as a result of the web's development at CERN, laying the groundwork for the current internet as we know it. The influence of CERN goes beyond its physical facilities. The company's open access policy has aggressively fostered global cooperation and information exchange. By making its discoveries and data accessible to the whole scientific community as well as the general public, CERN pioneered the idea of free and open access to scientific research. This dedication to openness and transparency has impacted scientific methods all across the world. In 2019, the LHC-B experiment at the facility made a discovery of a brand new category of particles called exotic hadrons. Instead of the 2 or 3 quarks that make up typical hadrons, these particles have 4 or more. The finding sheds light on the strong nuclear force and how matter is created. Takaaki Kajita and Arthur B. MacDonald were awarded the 2015 Nobel Prize in Physics for their understanding of neutrino oscillations, which was made possible by research done at CERN. Neutrinos have mass and can change flavors, as shown by the OPERA experiment at CERN's Gran Sasso Laboratory in Italy. This evidence helped to explain the phenomena of neutrino oscillations. A key component of CERN's scientific revolution has been its engagement in dark matter searches. Dark matter is an enigmatic type of matter that cannot be directly detected because it does not interact with light or other electromagnetic radiation. Its gravitational pull on material that is visible to the naked eye and the universe's overall structure, however, point to its existence. Uncovering the universe's composition and evolution requires an understanding of dark matter. CERN has been conducting experiments using cutting-edge methods and technologies to shed insight into the characteristics of dark matter. The Large Underground Xenon, or LUX experiment, is one of these tests, and it was carried out with the assistance of international researchers. Through the use of liquid xenon as a target material, LUX sought to directly detect dark matter particles. In order to protect the detectors from cosmic rays and other background radiation that can affect the readings, LUX was built deep underground at the Sanford Underground Research Facility in South Dakota, USA. Despite not finding dark matter particles, the LUX experiment placed strict constraints on their interaction strengths and helped to define a more limited range of dark matter's potential properties. The Alpha Magnetic Spectrometer, or AMS, is a noteworthy project carried out by CERN in the hunt for dark matter. The Advanced Microscopy Suite, a state-of-the-art particle physics detector installed on the International Space Station, is used to research cosmic rays, which are high-energy particles that are emitted from space. Since it began in 2011, the AMS has been a key component of the indirect hunt for dark matter. The AMS seeks to locate potential signs of dark matter annihilation or disintegration by measuring the cosmic ray flux and examining the data for excesses or anomalies. Our knowledge of the characteristics of cosmic rays and the particle makeup of the universe have both been enhanced by the data garnered by the AMS. Beyond these particular experiments, CERN's actively involved in dark matter searches. In order to better comprehend the dark matter, the organization actively supports and works with various studies and initiatives. For instance, the European Axion Search Experience, or CAST, is housed at CERN and aims to find hypothetical axions, which are possible candidates for dark matter. Axions are transformed into observable particles by CAST using powerful magnetic fields, which are then examined for signs of their presence. By hosting experiments like CAST, CERN offers the tools and experience needed for researchers to investigate further dark matter candidates. The continued scientific search for dark matter is evidenced by CERN's engagement, which demonstrates its dedication to answering some of physics' most challenging topics. Although the interaction features of dark matter particles have been constrained by direct detection experiments like LUX, the field is continually changing, and new experiments are being created to investigate other detection strategies and focus on a larger variety of probable dark matter candidates. The work being done by CERN to find dark matter not only improves our understanding of the universe's makeup, but also has wider ramifications. These investigations may reveal information that has consequences for particle physics, astrophysics, and cosmology as a whole. It has the potential to shed light on hypotheses pertaining to the creation and development of galaxies, the behavior of fundamental particles, and the fundamentals of gravity. Additionally, the technological developments produced in these experiments, such as very sensitive detectors, sophisticated data analysis methods, and space-based instrumentation, have practical uses outside of the study of dark matter. Over the years, the myths surrounding the development of black holes at CERN and the potential danger they bring to Earth has received a lot of attention. It's crucial to examine the scientific understanding of black holes, the security measures put in place at CERN, and the vast study produced by professionals in order to allay this worry. Black holes are exceptional celestial phenomena with powerful gravitational pull that are created when enormous stars collide. They are distinguished by their powerful gravitational fields, which prevent anything from leaving their clutches, including light. The worry surrounding CERN's research is based on the idea that stable black holes might form as a result of the high-energy collisions produced by the Large Hadron Collider, which could develop and ultimately destroy the Earth. However, misconceptions and sensationalism are mostly to blame for this worry. At incredibly high speeds, protons or other particles collide at the LHC particle accelerator at CERN. In order to study fundamental particles and their interactions, these collisions attempt to mimic conditions that existed in the early cosmos. Experts in science have done extensive safety evaluations to address the potential for black hole creation at CERN. These reviews include in-depth examinations and the fundamental tenets of physics such as quantum mechanics and general relativity. The scientific community as a whole agrees that the energies produced at CERN are insufficient to create stable black holes that could be dangerous. So, this is all about CERN and all the theories related to it. What are your views regarding the topic? Let us know in the comment section below. And if you enjoyed watching this video, make sure you like and share it. And don't forget to subscribe to our channel for more great, amazing videos. Thanks for watching.